Hello guys and welcome back to my channel. Today we are going to discuss our 12th chapter of data science, which is dimension reduction. The first topic of our dimension reduction is the need for dimension reduction. Dimension reduction is an important technique in data analysis where the dataset contains a large number of variables, making it difficult to visualize, analyze, or model. The main challenges associated with high dimensional data are curse of dimensionality, overfitting, computational complexity. As the number of features increases, the volume of the space increases exponentially, causing data points to become sparse. This sparsity can make it difficult to identify patterns and relationships. Overfitting. With a high number of variables, models are prone to overfitting, where the model fits the noise in the data rather than the actual patterns. This leads to poor generalization to new data. Computational complexity. More features mean more computation, increasing the time and resources needed to the train and evaluate models. Dimension reduction techniques aim to reduce the number of variables while preserving as much of the original data's information as possible. The result is a simpler, more efficient model that retains the essential relationship within the data. Now we are going to discuss multicollinearity. Multicollinearity occurs when two or more predictor variables in a regression model are highly correlated with each other. In such cases, it becomes difficult. Now we are going to discuss multicollinearity. Multicollinearity occurs when two or more predictor variables in a regression model are highly correlated with each other. In such cases, it becomes difficult to determine the individual effect of each variable on the dependent variable because their effects are intertwined. This leads to several issues in regression analysis. Unstable coefficients. When predictors are highly correlated, small changes in the data can lead to large changes in the estimated coefficients. Inflated standard errors. High correlation among predictors increase the variance of the regression coefficient, leading to wider confidence intervals and making it harder to detect statistically significant predictors. Misleading significant test. Multicollinearity can cause some predictor to appear insignificant when in fact they may be important, leading to inaccurate interference about the data. Now, identifying multicollinearity using variance inflation factors. Variance inflation factors is a popular diagnostic tool for detecting multicollinearity. VIF quantifies how much the variance of the estimate regression coefficient is inflated due to multicollinearity. It is calculated for each predictor variable by examining how well it is predicted by all other predictors in the model. The formula for calculating VIF is VIFI is equals to 1 by 1 RI square. Interpretation of VIF values. VIF is equal to 1, no multicollinearity. VIF is 1 is greater than VIF is less than 5. Moderate multicollinearity usually not a concern. VIF is less than 5, is greater than 5. High multicollinearity which may require remedial action. Now, principal components of analysis. Principal components analysis is a powerful method for reducing the dimensionality of data. PCA transforms the original variables into a new set of uncorrelated variables called principal components, which are linear combinations of the original variables. The components are ordered by the amount of variance they explain in the data. The goal is to retain as much of the original variance as possible while reducing the number of features. The process of PCA involves several steps in standardization, covariance matrix computation, eigenvalue and eigenvector computation, component selection. An application of principal component analysis. PCA has a variety of applications across different fields: image compression, finance, genomics. PCA can reduce the number of pixels required to represent an image while retaining the essential features. For instance, in face recognition, PCA can identify key features such as eyes, nose, and mouth, thus reducing dimensionality. Finance. PCA is used to reduce the dimensionality of financial data like stock prices, returns, or economic indicators. By using PCA analysis, analysts can identify underlying factors that explain the majority of the variance in financial markets. Genomics. In gene expression data, PCA is applied to reduce the complexity of high dimensional data, helping researchers identifying patterns in gene activity across different conditions. Now, how many components should we extract? When performing PCA, it is important to decide how many principal components to retain. This decision depends on balancing the reduction of dimensionality with the preservation of information. There are several methods to determine the number of components to extract. The eigenvalue criterion. This criterion suggests retaining components with eigenvalues greater than. The rationale behind this is an eigenvalue of less than 1 indicates that the component explains less variance than a single original variable and thus it contributes little useful information. The component with eigenvalue greater than 1 are considered significant because they capture meaningful variance in data. Now, the proportion of variance explained criterion. Another approach is to retain enough components to explain a predetermined proportion of total variance. Typically between 70% and 90%, this ensures that the retained components capture the majority of the variance in the dataset. While reducing dimensionality, a script plot can help visualize the proportion of variance explained by each component and guide the selection of the number of components. So our last topic is validation of the principal components. Validating principal components is crucial to ensure that the reduced representation of data is meaningful and reliable. Methods for validation include script plot, cross validation, explained variance. A script plot displays the eigenvalues of the components. A sharp drop after a few components indicates that the first few components explain most of the variance and additionally components contribute little. Cross validation. This involves splitting the data into training and testing sets, performing PCA on the training set, and then testing the performance on the test set to evaluate the generalizability of the selected components. Explained variance. After applying PCA, examining the explained variance ratio helps assess how much of the original data's variability is captured by the selected components. So guys, this is complete overview about our 12th chapter of data science, di- dimension reduction. So I hope you find this video helpful. If you find this video helpful, please like our video, subscribe our channel and share this video with your friends. Thank you for watching my video.